Machine learning models in healthcare can influence observed outcomes through one of two ways. By averting negative outcomes due to correct early intervention, as is the case for an early warning system, or by causing poor outcomes, like a resource allocation model, which incorrectly sends patients to the wrong hospital ward, allowing them to deteriorate. We focus on this second case as it causes performance overestimates, since some errors can appear to be correct predictions and leads to self-fulfilling prophecies. We refer to incorrect predictions flipping labels as error propagation. Model performance degradation resulting from updates on flipped labels is a phenomenon we refer to as error amplification. Standard threshold selection, where a score such as F1 is maximized on held-out data, can worsen error amplification, since it does not take into account the impact that the propagating error type will have on model stability. We propose modifying the typical threshold selection approach to simulate model updates and choose a threshold that gives the best long-term performance rather than the best initial performance. We show results on Mimic4 data here, and also have results on standard benchmark datasets in the paper. All experiments are done using fully connected neural networks. Models are retrained yearly. The figure on the right compares our threshold selection procedure against the naive approach of maximizing F1 score, with the proposed approach limiting degradation. The greater the capacity of a neural network, the more noisy samples it can fit. We hypothesize that higher capacity models are at greater risk of degradation. We can see this to be true in the figure where deeper models degrade much faster than shallow models. We consider how two popular regularization techniques, dropout and weight decay, affect error amplification since they can constrain model capacity. This figure shows that with sufficient regularization, a deep model will not degrade faster than a shallow model. Every time a model is updated, there is a chance for degradation. More frequent, smaller updates provide more chances for degradation to occur compared to less frequent, larger updates, even when the total amount of data used for both is the same. We consider two update strategies to test the effect of update frequency. On the left-hand side, we have data being accumulated over time, and on the right-hand side, a sliding window is used. The sliding window strategy is more susceptible to error amplification, and there's a clear advantage to using less frequent, larger updates in this case. Lastly, we investigate methods that can identify noisy samples by measuring the contribution of each sample to final model performance. Samples are ranked by their contribution, and the recall of flipped samples correctly identified is measured. Uniform label noise, where some samples have their labels flipped randomly, is much easier to identify than error propagation noise, where labels are flipped by model errors. Our work has examined a major challenge for deploying machine learning models, namely the introduction of bias into future labels through model errors. Changing existing procedures in the model development and deployment process is an effective way of limiting this phenomenon. While it's difficult to explicitly identify these biased samples, we show in the paper that some methods which implicitly account for label bias can further reduce error amplification.